And so begins lecture 6. We're going to look at the Euclidean algorithm and Bezout's theorem for polynomials. So let me start by just reminding you how we do polynomial long division. Now I should mention this lecture is, mostly the purpose of this lecture is to just show you that many of the things we can do for integers we can also do for polynomials. Maybe you've seen this before, maybe you haven't. If you haven't, it should be really kind of interesting just how striking the analogy is between integers and polynomials. So many of the theorems we have for integers just as well have a mirror in the theory of polynomials. So first of all, of course, we can do long division like this, right? And so if I take x to the fifth plus 3x to the fourth plus 2x squared plus 8, and I divide x squared minus 2 into it, I get x cubed plus 3x squared plus 2x plus 12. And you know that you're done once the remainder is of smaller degree than the dividing polynomial, right? And what's this whole calculation mean? It means that x to the fifth plus 3x to the fourth plus 2x squared plus 8 divided by x squared minus 2 is equal to this polynomial plus this, what we would call proper rational function, right? So the long division takes an improper rational function and it rewrites it as a polynomial piece plus a proper rational function, right? Where the degree of the numerator is strictly less than the degree of the denominator. And of course, number theory style, we repackage this as a multiplicative statement below in the green, right? You can think of a of x is equal to the quotient times the dividing polynomial plus the remainder, right? And what does the division algorithm for polynomials say? Well, the division algorithm for polynomials says, the way I'm going to state it anyway, is if the degree of the dividing polynomial is less than or equal to the degree of the divided polynomial, then there exists unique quotient and remainder polynomials for which a of x is equal to q of x, b of x plus r of x, where the degree of the remainder is less than the degree of the dividing polynomial, or the remainder is 0. Now, there's some funny business that goes on with the definition of degree. If you look at different books, you'll find out that they define the degree of the 0 polynomial in a variety of different ways. Some people say the degree of the 0 polynomial is -1. Some people say the degree of the 0 polynomial is minus infinity. Other people say the degree of the 0 polynomial is just not defined. So I went with the one that has the most shock value. I said, oh, I'm going to choose minus infinity. Why not? So see, the problem is the definition of degree in part is that it's the the leading coefficient that's non-zero that defines the degree, right? So what's the leading coefficient in the 0 polynomial? There are various formulas you write for the degree, which would break down if we didn't make this definition. But anyway, let me not belabor that here. So here's the division algorithm for polynomials, right? Basically that there exists a quotient, a unique quotient and remainder for a of x divided by b of x, all right? And here's the proof of it. Here's the proof of the division algorithm right here. So what you do, okay, now again, this is kind of a funny thing because I would say the actual algorithm is long division, but this is just that long division always works, essentially. I mean, there's an answer to find, right? So anyway, you define the set to be a of x minus polynomial multiples of b of x, and if 0 is in that set, then there exists g of x such that a of x is equal to b of x times g of x, so you can identify that the g of x is the quotient and the remainder is 0. All right. Otherwise, 0 is not in S, and we can let t be the degrees of polynomials that are in S. Right. Now that's a subset of the natural numbers in 0. So by the well-ordering principle, and this is, by the way, obviously non-empty, you can select a polynomial with least degree, which we will claim is the remainder. R of x is equal to a of x minus b of x q of x. And so that at least fits the bill. It satisfies the right equation, right? It remains to show that the degree of the remainder is smaller than the degree of the dividing polynomial. And we use contradiction just like we did in the case of integers, right? And I'm going to go through this somewhat quickly because I also, I don't really expect you to reproduce this on the test or anything. I'm showing it to you for logical completeness, not because I expect you to, to replicate this in a time test. That would be. I want you to know how to explain it if you had a student who was curious. All right, and so I'm showing you, so now you know at least one place you can look it up, right? It's in pretty much every good abstract algebra book. Like if you look in, for example, here's a book I use as an undergraduate, Contemporary Abstract Algebra by Joseph Gallian. It's in there, the proof I'm going through. Actually, I didn't get this proof from there, but he does have a proof in there, for example. Anyway, me focus here. So suppose towards a contradiction, the degree of the remainder was larger than or equal to the degree of the dividing polynomial. Okay, so that means we can write r of x like this, and we can write b of x like that with these coefficients, the leading coefficients being respectively r sub n and b sub m, where n is larger than or equal to m. That's the contradiction, right? The degree of the remainder is larger than the degree of the dividing polynomial. And this will lead to a contradiction. Here's how. So first of all, if we define r bar of x to be r of x minus the, and so what this is doing is it's peeling off the leading term in b of x, I suppose, and it's converting it to the corresponding leading term in r of x. So this is basically canceling out the leading term in r of x with the leading term in b of x. That's only possible because x to the n minus m is a positive given that assumption, right? So that's what this assumption is what's powering this construction. And so the r sub n, x to the n's cancel, and it leaves you with this polynomial here, which has degree n minus 1. But unfortunately, well, fortunately I should say, r bar of x, this guy right here, is again something of the form a of x minus b of x times a polynomial. So it's an element of s, but it's an element of s with smaller degree than the element of smallest degree, which of course is a problem. So this is a contradiction to the well-ordering principle construction here, and therefore we get that the degree of the remainder is less than the degree of the dividing polynomial. And I will spare you the details of uniqueness, but you can prove that the quotient and the remainder are unique, again by a little calculation, similar to the one we did for integers, actually. Okay, so there's that. Now, what else can we say about polynomials? Again, there's a lot of analogies between polynomials and integers. Let's continue down this path. Let's see what else we can say. Now, once we get through all these analogies and so forth, we're actually going to apply this to a problem of high school algebra that you're probably all familiar with, the problem of rationalizing a fraction. All right, so we're gonna look at how these polynomial ideas help us to rationalize a fraction. That's kind of surprising. Hey, the secret word for this lecture is surprising. Okay, so a of x divides b of x if b of x is a multiple of j of x, but here we're allowed to multiply by a polynomial, so it's a polynomial multiple, all right? In this case, we say b of x is a multiple of a of x, and we also say that a of x is a factor of b of x, all right? So everyone's factored, so, right? We got the factor theorem. F of x is a polynomial, then x minus c is a factor of f of x if and only if f of c is 0. That is proved using the division algorithm, right? So if x minus c is a factor, that means f of x is a multiple of x minus c. So when you plug in c, you get 0. That's the forward direction of the biconditional here. The reverse direction, conversely, suppose f of c is 0, then by the division algorithm there exists a quotient and a remainder, but here by the counting, the remainder has to be a constant since the dividing polynomial is first order. So either r is 0 or it's 1, or it's a constant rather anyway. But it's a constant, it could be 0. Okay, but setting x equals to c, we get f of c is q of c times c minus c plus r, which is just r, but that's by assumption 0 here. Therefore, we find that f of x is a multiple of x minus c, which is to say x minus c is a factor, or in other words, f of x is divisible by x minus c. All right? So all that divisibility language we talked about for integers also works for polynomials. Now, the polynomials have a fundamental theorem. We haven't seen the fundamental theorem of arithmetic yet. That's upcoming in a soon coming lecture, right? So we will soon talk about how you can take integers and you can factor them into a product of primes, possibly repeated. The analog of that for polynomial algebra, of course, is the fundamental theorem of algebra. And the fundamental theorem of algebra simply states this, that if you factor a polynomial into a product, you can factor it into a product of linear factors over the complex numbers, right? In other words, and there's more than we can say. If you have, on the other hand, a polynomial with real coefficients, then each complex factor is paired with a conjugate pair, right? And so a real polynomial factors to produce, I'm missing a, thus real polynomials factor, I missed the S there, real polynomials factor to produce, I'm missing maybe like a word like a product, I don't know, the grammar is a little bit off here, sorry about that, to a product of real linear factors x minus c and quadratic factors x minus alpha plus x minus alpha squared plus beta squared, and of course both of these could be repeated, but that's it. So you can always, at least in principle, factor a polynomial, a real polynomial, into a product of linears and quadratics, right? We know this. And the completing the square method we went over will reveal whether or not a given quadratic can be reduced or not, right? When you complete the square on the quadratic, if you get a plus, it's a complex. If you get a minus after the dust settles, that's one that can be factored over the reals. So the proof of the fundamental theorem of algebra is definitely beyond this course. Gauss found a proof in about 1800. I think Gauss found, if I remember right, like several proofs of this over his lifetime. And the proof is not just algebra. You need some kind of like analysis in the sense of like calculus and limits and all that kind of thing. The smallest amount of analysis I've seen used in the proof, there's a proof that you can give in what's called Galois theory, where the analysis needed is basically just the intermediate value theorem. So that's pretty minimalistic. A proof which uses a lot less algebraic sophistication but much more analytic sophistication is found in complex analysis, which I'm teaching this semester actually. But so anyway, if you look at the complex analysis course, you can find a proof of the fundamental theorem of algebra. So just mentioning that, it's not a terribly easy thing to prove actually. So, but we've had a solid proof for it for about 220 years at least. So here's some examples. These should be relaxing, all right? I really should have assigned more homework like this, right? Okay, so if a real polynomial f of x has minus 2 plus 3i as a 0, that means that x minus that and x minus its conjugate are both factors of f of x. And so when you multiply those out, the imaginary part cancels out, and you're just left with x plus 2 squared minus 9i squared. But remember, what's the deal with I squared? I squared is minus 1. So that gives us the plus 9. There's that irreducible quadratic, or sometimes people might call it a. So it, terminology varies. Some people call this a prime quadratic. I prefer the terminology irreducible, which is kind of just a fancy way of saying you can't factor it over the number system that you're working with. Irreducible quadratic. Now, if you talk about an irreducible quadratic, obviously you're not talking about the complex. You're not allowing yourself the flexibility of complex factorization, right? Because if you have complex numbers, you can factor it, all right? But anyway, I haven't told you what the formula is for f of x, but this knowledge, right, that's a 0 is enough to say that this quadratic is a factor of it, all right? Here's another example. Here's a formula, x cubed plus 3x squared plus 9x minus 13. Say factor this completely given that f of minus 2 plus 3i is equal to 0. All right, so wait a minute. So by example 2, we know that x squared plus 4x plus 13 is a factor, right? So if you know something's a factor of a polynomial, a good strategy for finding the cofactor, if you will, is just to use division. So here it is. So if I divide x squared plus 4x plus 13 into this cubic, I get x minus 1. Therefore, the remainder is 0. That's good. It should be. If it's actually a factor, the remainder must be 0. And there we have it. X cubed plus 3x squared plus 9x minus 13 is the product of x minus 1 and x squared plus 4x plus 13. All right. Now, I think it's unfortunate. Some people have gotten in the habit of just teaching synthetic division. I think it's not wise, because synthetic division, it's not natural to divide higher order polynomials with synthetic division. And I just think long division is an important skill that we should all have. So if that's not the case, we should put it back in the curriculum. Just saying. Now, so f of x, here's the same polynomial, but this time I'm like, wait a minute, f of 1 is 0, which is easy enough to check, right? 1 plus 3 plus 9 minus 13 is 13 minus 13, which is 0. So that means, by the factor theorem, x minus 1 is a factor, right? So you could do this with synthetic division, but I won't, because I don't believe in synthetic division, honestly. So here's the long division of x minus 1 into that, which gives you, again, a remainder of 0, and there's your quotient. So, I don't know, maybe you thought about this before. Maybe it wasn't emphasized in your algebra class, I don't know. But we can use division for factoring is my point here, okay? I don't think I've really assigned you homework on that, unfortunately, but maybe I will. Let's see here. But I think I have to, well, anyway, let me shut up. All right, so definition. If we have polynomials, a of x and b of x, the greatest common divisor of a of x and b of x is a common divisor, and it has to be monic just to make it, that gives us a unique choice. Monic means the leading coefficient is 1. So is the monic polynomial of highest degree, for which is a divisor of both a of x and b of x. Okay, so just like with numbers, we could use a prime factorization to figure out the GCD. You could do something similar with polynomials, right? Like if I had b of x was this, and I had a of x was that, so like x minus 1 times x plus 2 times x squared plus 1 times x minus 4, x minus 1 squared plus x times x plus 3 times x squared plus 1 times x minus 4. You can look at this and you can see, aha, I've got common divisors of x minus 1, x squared plus 1 is common, x minus 4 is common. So if I multiply these together, that gives me the greatest common divisor, actually, which is, it works out to this when you multiply these out, okay? Now, the explicit form of b of x and a of x is up here in red, if you multiply these out, right? I think I used Wolfram Alpha to do this because I didn't want to make a mistake, So, great. There's another way to do this, though. So if we have a of x is equal to b of x, q of x plus r of x, then guess what? The greatest common divisor of a and b is the greatest common divisor of b and r. So this goes to show you that division of polynomials can nicely simplify the GCD calculation. Let's see how it goes. So like, the division isn't hard here. Like, to divide this, all right, which is, by the way, b of x, into a of x, there's only one step, right? X times this gives me that. Not really, it gives me this, which when we subtract the second from the first, we get minus 3x to the fourth plus 15x cubed minus 15x squared plus 15x minus 12. And now that's not quite the GCD yet, but so the last non-zero remainder will be the GCD. I know there's only one step here, so it's kind of hard to appreciate what I'm saying. I think I have an example upcoming where there's more than one step, but I don't know. It's difficult to come up with examples that have as many steps as like we had for the Euclidean algorithm for integers, but there is a Euclidean algorithm for polynomials. And anyway, so if you divide by minus 3, it's exactly that. So I have to divide by minus 3 to make this monic. To get the leading coefficient to be x to the fourth, I have to divide this by minus 3. And when I do that, I get like 15 over minus 3 is minus 5. Minus 15 over minus 3 is 5. 15 over minus 3, minus 5. Minus 12 over minus 3, 4. Okay? So you can either find the complete factorization of the polynomials to figure out the GCD of them, or you could use division, right? Or better yet, we could use my brother's website and be lazy. So here's another example. To calculate the GCD of x to the 7th plus 3x plus 2 and x squared minus 1. All right, let's get to it. So what we're going to do is we're going to divide x to the 5th, x squared minus 1 into x to the 7th plus 3x plus 2, right? And when I do that, I get x to the 5th plus x cubed plus x when you go through the steps, right? The remainder is 4x minus 2. So this time I can do what? I can divide the remainder into the dividing number for my next step. See, in the previous one, I couldn't have done that because, like, there's nothing really interesting to do. The remainder, let's see here. Sorry, I don't have the words to explain what I'm saying at the moment. Let's see here. What's the difference? So here the remainder was linear and the dividing thing was squared. Whereas in this one, the Sorry, I don't. Missing some words here, guys. Sorry about that. Anyway, so here's the next one. So I divide 4x plus 2 into x squared. So I divide this into that, and I get that. And then the remainder is 3/4, right? And I guess at that point I'm done because I've got to that there. Let's see here, and then here's a horrible calculation. So I can take, from these two, I get this equation and that equation, right? I get x to the 7th plus 3x plus 2 is equal to x squared minus 1 times that plus 4x plus 2, that's the remainder. And I get, from this one, I get x squared minus 1 is equal to 4x plus 2 times the quotient, which is 1/4 x minus 1/8, and that's equal to minus 3/4, right? So if I take the second equation and I multiply by minus 4/3, I get this, all right? And then back substituting, I can solve this for 1 equals to that. And then I can take this 4x plus, excuse me, I can take this, let's see here, I take the, where'd it go? I take the x squared minus 1, and I, no, that's not what I do. Oh, I'm very bad at this back substitution thing, guys. Sorry about that. What's going on here? What did I get rid of? I kept the 4/3 x squared minus 1. And when I go from here to here, what did I do? I kept this factor, that's over there, right? So it must be that this 4x plus 2 is replaced with what's in the square brackets, soon to be green. So this guy here is coming from that. Where's that coming from? That's coming from solving this 4x plus 2 for all of that junk. See, x to the 7th plus 3x plus 2 minus x squared minus 1 times that. All right, and then once you've got that, if you tilt your head and squint, you can rewrite it as that times x squared minus 1 and that times a of x. So this is Bezout's theorem. Bezout's theorem says that the GCD is, in this case, a polynomial linear combination of a of x and b of x. So here are the u of x and v of x. These are the Bezout coefficients in this context. And there it is. Now, let's see here. Bill Cook Math website. So thankfully, there is a help for this. If you go to Bill's website and you go to the all demos and you scroll down here a bit past all of his calculus jibber jabber, eventually you get to Euclidean algorithm and some algebra demos. And see, here's Euclidean algorithm for polynomials. All right, and he explains why it's true here. And then you can put polynomial. You can change this here and here, and I'll hit update. And this is why I should have got my wife's tablet, because this thing is too small. Come on, flip over. Doesn't know what's good for it. So this is miserable, but if you can find a proper thing to work on, you can. It has the division steps, right? And it also has the GCD, and it also has the Bezout coefficients down here, which, see at the bottom it actually has the coefficients. So that's how I was able to check my work here. I use this here to check that. For the sake of time, and also because my phone is miserable to look at, I won't show you in this video, but I hope that it's pretty straightforward to use. I don't think you'll have a problem with it. So I do not advise this calculation without technology, by the way. All right, but if we do have the technology, then we can find these kind of identities. And so if we get curious about certain questions, we can use this polynomial algebra as a means to solve some pretty interesting, well, I'm not sure interesting is the right word, but pretty surprising problems, I would say. So let's get just back to the problem we have in, I don't know, middle school math. I'm not sure where it first comes up, but suppose the problem of rationalizing, right? You get 1 over 2 plus square root of 3. How do you get that square root out of the denominator? How do you do that? Well, we all know the trick. You just change the root to minus the root, keep the other number the same, and multiply by what you might call the conjugate over the conjugate, right? And in so doing, the 2 root 3 and the minus 2 root 3, they be canceling, and you get 2 times 2, which is 4, and the square root of 3 times the square root of 3, which is 3, but there's a minus, so we get 4 minus 3, which is just 1. And so if you want to rationalize this fraction, you can, and what you get is just 2 minus the square root of 3, which is pretty neat, right? I mean, it almost seems wrong, right? If you want to convince a student, what do? You show them it works in the calculator, because that's what they believe, right? So 0.2679, and let's try 1 divided by parentheses 2 plus the square root of 3. 0.2679, what do you know? So, in fact, this thing even knows that it rationalizes like that, right? This calculator actually will rationalize reciprocal fractions. So, now, on the other hand, what happens if we try to do the same with the cube root? So, when somebody first asked me about this, I was like, oh, well, you just multiply by the conjugate over the conjugate, right? This is what every person with a little bit of math confidence will tell you. But it's an unfounded confidence, because when you actually try to work it out, to quote my community college professor, this dog does not hunt. So like the cube roots downstairs, they don't cancel out. So you still got cube roots, or if you read in Asian math books, they tend to call these surds. A radical is a surd. So you got your surds in the denominator, and that's not where they belong. So how do you fix that? How do you rationalize the reciprocal of a sum involving a cube root? Well, there is a way to do it if you use a little bit of clever polynomial algebra. Here, I'll show you. So here's the strategy. We notice, if we want to deal with the cube root of 3, we notice that x cubed minus 3 has the cube root of 3 as a solution, right? So if we put x equal to the cube root of 3, what we're interested in, this problem we just phrased up here, right? We're trying to find the reciprocal of 2 plus the cube root of 3, right? So if x is equal to the cube root of 3, we're trying to look at 2 plus x, right? We're looking at 2 plus x. That's what we're trying to gain understanding of. And so what to try? Well, what if we divide x cubed minus 3 by x plus 2? What happens then? What does that reveal? It reveals much. It reveals much. See, because what happens when you do that calculation, I'll show you up here, is that we get that x cubed minus 3 times x plus 2 times, well, the quotient x squared minus 2x plus 4. So x cubed minus 3 is equal to x plus 2 times this x squared minus 2x plus 4 minus 11. But what happens when you plug x equal to the cube root of 3 into this equation in red right here? Well, the x cubed minus 3 is gone, so move 11 to the other side. We've got 11 is equal to the number we're trying to find the reciprocal of, 2 plus the cube root of 3. And this other thing over here, I don't know what to do with that, but it's there, right? So then solve for 1 over 2 plus cube root of 3, and there you have it. We rationalized the fraction just like that. So there's a method. What you can do is just create a polynomial which has the root you're interested in as a 0. And then think of x as being the thing you're trying to gain traction on. And then you just create, in this one I did 2 plus x. I think I've got another example so you can have a little bit of variety here. Let's see here. Yeah. Here's another one. So, all right, so this one we're going to try to rationalize fifth root of 2 over 3 minus 6 times the fifth root of 2. All right, so my first move is like, okay, so x to the fifth minus 2. That's my that's my polynomial that's 0 when I plug in the fifth root of 2. Right? Great. And I'm after 3 minus 6 times the fifth root, so that's going to be 3 minus 6x for the polynomial that I want to divide into x to the fifth minus 2. And so the GCD of x to the fifth minus 2 and 3 minus 6x is 1. And courtesy of Bill Cook math website, magic. Which, if you didn't have Bill's website, right, or if you thought Bill had nefarious, if you grow suspicious of my brother, if you think he's trying to somehow plant viruses on your machine and then like take your personal data, whatever nefarious means my brother you might ascribe to him. The good news is these problems you could just do long division. It wouldn't really be that hard. Getting this 1 over here, you have to multiply by like an ugly fraction, but honestly you could see from the previous problem that like long division is probably going to do it for most of these. Anyway, so from Bill's website, the Bezout coefficients for x to the fifth minus 2 and 3 minus 6x are minus 32 over 63. And this thing, okay. And when we plug in x equal to the fifth root of 2, what happens? This is 0. And we get a number times the number we're trying to calculate the reciprocal of equal to 1. So divide that to the other side. Voila. There's the answer. 1 over 3 minus 6 root 5, the fifth root of 2, is equal to minus 1, minus 2, fifth root of 2, minus 4, fifth root of 4. See, if you square this, the fifth root times the fifth root of 2, it gives you the fifth root of 2 times 2, which is 4. And likewise, 8 and 16 here. Now that's not the answer yet, right? Because this one, I had this pesky fifth root of 2 up on the numerator, which I've been ignoring. Because that's already where it belongs, right? So leave it there. Do the math, and then circle back, and oh, sorry, I've told you to circle back. This was supposed to be an intelligent lecture. My apologies. So the go back and multiply the fifth root of 2 times that, and what happens is the fifth root of 2 times the 16 term, that gives you back a 2 again. So like the fifth root of 16 times the fifth root of 2 is the fifth root of 32, which is 2. And so that's where this minus 16 times 2 gave me this minus 32 at the start, and then the rest of these are just, so that minus 1 goes to this root 2, fifth root of 2 goes to the fifth root of 4, that minus 4 term goes to this minus 4 term, that minus 8 term goes to that term, and you got this 189 underneath. So, yeah. So, I don't know. I think these are pretty neat. It would make a kind of interesting lab for students to, like, practice long division and maybe do something surprising. Because I think if you asked high school students to just find how to rationalize something like this, I don't think, I mean, I think I've met in my lifetime about 3 students that I think have the mental capacity to do this without theory. And I've taught thousands of students. Like this, getting from here to here without some technique, that would be tough. That would be really tough. Okay, so, and then one last thing. There's another way to rationalize polynomials, and it's through something called Galois theory. So one of the things I should mention, as we study number theory this semester, I like to talk a little bit about history, right? So at the end of the 18th century, we had the work of Euler and then Lagrange, and we were, they had solved, so the ancients had solved the quadratic, right? And in the 14th and 15th century, somewhere in there, the solution to the cubic kind of shook loose. And shortly thereafter, the solution to the quartic shook loose. And then incredible effort was made to solve the fifth order problem, to reduce it to a solution in terms of radicals. And it failed, all right? So like they couldn't do it. I mean, they tried and tried and tried. But then at the turn of in the 1800s, the early 1800s, it started to become clear to the mathematical community that you couldn't find an analog of the quadratic equation for like a fifth order problem. And so Abel was the first to probably to prove it. Most people would agree. And then about 10 years after that, in about 1830 or so, Galois came up with what we now call Galois theory. And Galois theory not only explains which quintic polynomial equations can be reduced to radicals, it tells you which ones cannot. And it's really the birth of what we would call modern group theory. So all of that in about 1830 by a guy who, I think he died at 19 or 21, something like that, in a duel. But and then, of course, the other place where group theory came up was in the study of symmetries. But tremendous progress in mathematics, of course, during that time, and still today. But that's what I'm talking about. This Galois theory. It's somewhat old. It's 1830s. It probably was not really. It's been refined since then, of course. But here's just a simple example that you would find in the theory of in Galois theory. And so, I mean, if you're curious about Galois theory, if you get any abstract algebra book, you can. There's always like a chapter on it way in the back here. See, like, oh, sorry. This is again like chapter 32 in Galileans on Galois theory, and of course that's not a full treatment. I mean, you really should have a whole course in this stuff, right? It's pretty tough as things go, but some of the ideas are relatively simple, and I think you can understand them even now. So here it is. So the concept of complex conjugation, right, is the first example of what's called a Galois conjugate. So if you think about it, the way we, calculate the reciprocal of a complex number, what do? We do 1 over z, and we do the complex conjugate over z times z bar, right? And it turns out that that is, x minus iy over x squared plus y squared. So this is the magic of the conjugate trick, is it makes the denominator into something real. And similar things happen, like I was just showing you in the previous, back here, right? Back. So same idea here, right? Multiplying by the conjugate made this go from something with radicals to something without, right? So it turns out that when you study more complicated examples, like for example this one, if you have a number field which includes the square root of 2 and the square root of 3, then if you look at what's called that's actually what's called the splitting field for x squared minus 2 and x squared minus 3, because it completely factors in that field. And in this number system, you have numbers of the form a plus b root 2 plus c root 3 plus d root 6. Here a, b, c, and d are all rational numbers. And in this context, there's not 1, not 2, not 3, but actually 4 Galois conjugates. And here's the formulas for them. Epsilon, alpha, beta, and the composition of alpha and beta is the fourth one. So epsilon does nothing. See, epsilon of x is just equal to x. All right. Alpha, it swaps the sign of the square root of 2 to minus root 2, so that also does that over here, because remember, root 6 is square root of 2 times the square root of 3, so like if it changes 2 to minus root 2, it changes the sign of 6. And likewise, beta swaps the sign of root 3 to minus root 3. And so anyway, basically when you study the theory of all this, the Galois conjugates have to send these roots to these roots because of what the Galois conjugates are. They're a so-called automorphism of the field. And so anyway, these are the 4 possible automorphisms of the splitting field. And the cool thing is, when you multiply them all together, right, and I just shoved this into Wolfram alpha because, life is too short. When you multiply these all together, there's no radicals in the answer. It's just, see that? It's just a product of terms of 4th order. Everything in here has got, well, there's the one that feels to me like a mistake. That feels wrong. I bet that's b to the 4th. So I wouldn't worry too much about that. I was in a hurry, but you know what? I'm just going to go ahead and I'm going to put a 4 on that. That's most likely what I did wrong. Okay. Anyway, so that's the product of all these, and usually you call that, like, they'll call it the norm of x. All right. So the norm of x is an integer, as it happens, and so you can do the conjugate trick. See, like this. So suppose you want to conjugate that. That's what I'm calling that thing x. So you do 1 over x, and what you do is, well, x is equal to epsilon x, right? X is equal to the identity conjugate on so the identity. That's by definition up here, and so this is equal to that, and then I just divide and multiply by the 3 other Galois conjugates in this case. And okay, so it turns out that this mess up here just simplifies to 4 for this number. And when you multiply these out, I used Wolfram alpha, you get that. So this is the other way you could rationalize more complicated square roots and such. You could find the corresponding number field, which serves as the so-called Galois extension. But this is definitely a wrong way to teach high schoolers, right? For sure. Because, well, anyway, I just think this is not the right way. I think the polynomial trick I showed you is more fun. But anyway, so just some recreational mathematics for you there. I don't think this is something I can reasonably test on, obviously, because it takes, I don't know, 2 months at least to really do Galois theory properly, and even that's debatable. So anyway, thanks guys. That's it for today.